In this video I want to talk about multipliers. So you know how to multiply decimal numbers. So let's just take a look at one example. Let's just say we want to multiply 230 by 42. So what we basically do is first multiply 230 by 2. So we have 2 multiplied by 0, which is 0, 2 multiplied by 6, which is 6, 2 multiplied by 2, which is 4. So 2 multiplied by 230 is 460. And then we shift one place to the left and multiply the above number by 4 now. So 4 multiplied by 230, it is 920. And the reason that we shift is that this is basically having a weight of 10. So what we actually do is that we calculate the multiplication of 40 by 230. And then what we do is that we sum these two numbers together. So the final result is 9660 or 9660. So we can do the same for binary numbers too. So let's just say we want to multiply 0101 and 0111. So 0101 it is 5 in decimal, and 0111 is 7 in decimal. So the final result should be 35. So we basically do the same as we did here. We first take the first bit of the bottom number, multiply it by the one on top. So we have 1010, or more accurately 0101 as the result of first level. Then we shift one place to the left and do the same. So here we again have a 1. So it is going to be 0101, and this one is basically, you can say it is 0. And then you shift one place more to the left. Multiply this 1 with 0101, which is again 0101, and then finally multiplying this 0 with the value, which is going to be 0000. And then what we do is that we calculate the summation of these four partial products that we have. And if I calculate the summation, you see that the final result is actually 35. You see, this is the 6th bit that has a weight of 2 to the 5. This one has a weight of 2 to the 1, and this one has a weight of 2 to the 0. So one thing that you should notice is that when you multiply 4-bit numbers together, the final result usually cannot be contained in 4 bits. So you need to account for that. But other than that, the procedure is very simple. So I said that for creating the final result, we have to form partial products. Partial products for multiplying decimal numbers acquired by multiplying a single digit of the multiplier with the multiplicand, right? And then we shift everything one by one to the left, and then we sum all of the results together. But the whole point of the circuit that we want to create here is a multiplier circuit. So if we know how to do the multiplication, right, why don't we do that already, right? But with binary numbers, something that is noticeable is that this result, right, since the values that we can have for each bit is either 0 or 1, this is either an exact copy of the above number or it is all 0. So if this value is 1, you have an exact copy. If this value is 0, like we do here, you have all zeros. So how can we achieve that? By ANDing the bit with all the bits of the above number. So if I calculate the AND of this bit with all these individual bits, I basically can have an exact copy if the bit that I want to find the AND bit is 1, or I get all zeros if the bit is 0 to begin with. So that's how we can create multiplier circuits using the concept from digital logic. So the general schematic of a multiplier circuit looks something like this. So here I want to show you the internal parts of a 4x4 multiplier. So we have input A, which has 4 bits, we have input B, which also has 4 bits, and we have output P, which has 8 bits. Because the result of multiplying two 4-bit numbers need at least 8 bits to be represented. You might ask how or why, because the largest number that you can represent with a 4-bit value is 15. So 15 multiplied by 15 is 225, right? And for representing 225, you need at least 8 bits. So let's just go through the process one more time and see how it can be done. So we have A3, A2, A1, and A0, basically the bits of value A in order, and then B3, B2, B1, and B0, the bits of value B in order. So as I said, what we do basically is that we take 1 bit of the second value and we AND it with all the individual bits. So if this bit is 1, that basically creates an exact copy of the above number. If this value is 0, that makes a number all 0 with the same number of bits as the above number. So we have, for the first level, A0, B0, this is the AND, and then A1, B0, A2, B0, and A3, B0. Then we take B1, we shift it 1 place to the left and repeat the process. Then we take B2, shift 1 place to the left, repeat the process. And then finally for B3, we shift 1 place to the left and repeat the process. And then what we need to do is that we need to calculate the result of summation. So for P0, it is going to be only A0 and B0. For P1, it is A1, B0 added with A0, B1. And if we have any carry on, we have to consider that one too. For P2, it is the result of adding these 3 numbers with a carry from a previous stage if there is anything. So we have a sum bit and a carry out, and then the process is the same for all of the other ones as well. So if I want to create a circuit, a schematic for such circuit, this is what I have. So each one of these units, if you remember from before, is a full adder. It is there to add 2 1-bit numbers in addition to having a carry in from a previous stage. So for this one, for P0, as I said, it is going to be the result of ANDing A0 and B0 itself. For P1, it was the result of adding A1, B0 and A0, B1. And that's actually these 2 terms that are created here. Of course, for this we don't have any carry in from the previous stage, but if we have a carry out, that is going to be added to the value of the next stage. And then this process is going to be repeated until the final value for the multiplication of these 2 4 bits is calculated.